Dear students, let us begin the third part of the lesson, in which we will be learning about the computation of chi-square statistic and inferences with the same. To compute these chi-square statistics for goodness of fit, we will follow these steps. Coming to the first step, you have to set up our hypothesis, that is our null and alternate. Null hypothesis H0 can be framed as the observed data follows the Poisson distribution. As I mentioned in my earlier lessons, while writing your null hypothesis and alternative hypothesis, you have to be concentrated on the problem. That is, the observed data follows the Poisson distribution. You have to concentrate the statement relevant towards your problem. Defaultly, your alternative hypothesis H1 will be the observed data does not follow the Poisson distribution. Now coming to the step 2, choosing the level of significance alpha for the test, which has been commonly used as 0.05 or 0.01, that is 5%, 1%, or you can go with the 10% also. Calculate the expected frequencies under the Poisson distribution. For each category or interval, compute the expected frequency using the Poisson probability mass function, that is your EI can be calculated with n into p x equal to xi. That is your n will be representing your total frequency here, where your expected frequency EI will be taking as E1 will be for your first expected frequency, E2 will be for your second expected frequency, you can extend as like. Whereas here the n is your total sample size and p of x equal to xi will be the probability of category for ith according to the Poisson distribution. Next, coming to the step 4 here, calculate the chi-square test statistic using the following formula here. You can see over the chi-square formula, where the first symbol represents the summation here, which means that then OI minus EI whole square by EI. As you know that every time you are writing the statement as there is a significant difference between observed and expected frequency, that is the difference you are doing here, OI minus EI whole square divided by EI, that you are representing here as a formula. Now this is your summation symbol here, where your OI is your observed frequency for category I and EI is your expected frequency for category I. Here while calculating this chi-square statistic, where you can obtain your calculated value. Next, you need to go for the degrees of freedom, as in the degrees of freedom can be calculated with number of categories minus 1, that is n minus 1. Then you can go for your comparison. Chi-square calculated value will be compared with your chi-square critical value with respect to the degrees of freedom and chosen significant level. Based on this, you can go for your comparisons, whether you are going to accept your H0 or reject your H0. So here in a chi-square statistic, if your calculated value is greater than the critical value, then we will be rejecting the null hypothesis. It means that you have been concluding that the observed data does not follow the Poisson distribution. That is, you are going to accept the alternative hypothesis. If you have been computing the chi-square statistic, it has been becoming as less than the critical value, then you will be failing to reject the null hypothesis, and you can conclude that the observed data does not provide enough evidence to reject the assumption that it follows the Poisson distribution. Whereas here in these two situations or in the two decisions, you are able to identify whether the data has been suitable for the Poisson distribution or not. It means that it has been properly fitted or not properly fitted can be identified. As I mentioned that Poisson distribution will be an pattern that it will be following a rare type of cases. As we mentioned in our previous examples, as in a website traffic or maybe in a medical data, the Poisson distribution will have a rare type of situations. For this case, whether it has been following or not can be identified through these decisions. Now I can go with an next situation as here. Remember that the chi-square test assumes certain conditions such as independent observations and adequate sample size. You know that the chi-square is having some default assumptions to be followed. In that particularly, the sample size will plays a major role, because if you have been chosen with an less number of sample, automatically you may be facing the accuracy of the results in a problem. That is that your sample size has to be in a large, then only you can move on. Similarly, you can also move on in an expected frequency, the each expected frequency has to be greater than 5 is a default condition. It cannot be less than 5. Even though if you have been having less than 5, you have to combine those expected frequencies. So again one more assumption that independent observations, where the observations has to be independently chosen, where you cannot identify or found any dependency in nature. You can also interpret the results should consider the practical significance of any deviations observed. So without your practical significance you cannot interpret your results, because whatever the problems or whatever the data sets you have been working, it has to be in a practical significance, where you have to identify what will be the application for its real time. Now we can go for a problem here. You can understand how you have been Poisson distribution will be used here. You can see when the first proof of 392 pages of a book of 1200 pages were read, the distribution of printing mistakes were found to be as follows. That is, a book has been printed with mistakes. They have been specified as number of mistakes in a page, that is started from 0, 1, 2 up to 6 here. Then number of pages, they have been went with 275, that is 0 number of mistakes obtained in 275 pages, 1 mistake identified in 72 pages, 2 mistakes identified in 30 pages. In similar way 6 mistakes has been identified in 1 page. Now we have to fit a Poisson distribution for the above data to test the goodness of it. As I mentioned that the Poisson distribution will follows the rare event. It means that you have been moving towards number of mistakes in a page. It means that you are calling it as the rare event here. Just you can go on with an defaultly first you will calculate the mean here x bar, that is summing up of all the values divided by the total frequency, where you can obtain the value as here 0.482. Then to fit your Poisson distribution you have to move with your mean, that is x bar, already mentioned as the mean, variance and parameter, all the three will be same, that is 0.482, where you can multiply your total frequency towards your Poisson distribution, that is capital N into P of x. Your capital N is 392 multiplied by e to the power of minus lambda. The lambda is nothing but your 0.482 lambda to the power of x, that is 0.482 power x by x factorial. Whereas here your values can take as 0, 1, 2 and so on up to 6, because you have been having the maximum mistakes as up to 6. To calculate you can substitute each and every value 0, then you can substitute your 1, you can substitute your 2, 3, and by substituting you can get all your probability values, and you can multiply the probability values with your total frequency as 392. Then you can obtain your expected frequencies. So which has been displayed in a table at the end here, capital X, that is number of mistakes 0, 1, 2, 3, 4, 5, 6, and the expected frequencies has been given as here as the values as here you can see 242.1, 116.7, 28.1. Similarly you can see these set of values. So here you have been obtaining your expected frequency through the distribution, that is your Poisson distribution, where in this Poisson distribution you are having a mass function as like here probability mass function, that is nothing but e power minus lambda, lambda to the power of x by x factorial. So here you are using the term as an r, so r factorial. It means that here your probability mass function will be defined as like this here by substituting your observed frequencies, where you can obtain your respective expected frequencies. That what listed here in your table. Now after computing this calculation, default you have to move towards your calculation of chi-square test statistic. So here you can see the observed frequencies as listed here 275, 72 listed as here. Then you have obtained your expected frequencies and you have been listed as a table. Just now I have been mentioned that your expected frequency should be greater than 5, it cannot be less than 5, whereas see here it is less than 5, 4.5. When you are having the values less than 5, then you have to combine those values while till getting your greater than 5. You can see here 4.5, 0.5, 0.1, 0. All these 4 values are less than 5, hence you are combining all these values into a single one, that is 5.1, and we have been obtained it as an more than 5. Similarly you have to do the same for your observed frequency defaultly. Here there is no particular condition, whatever the expected frequencies has combined, the same observations has to be combined in the observed frequency. You can see here 7, 5, 2 and 1. So here you have been combined these last 4 values, the same last 4 values has to be combined here. Then you can go for your calculation of observed and expected frequency OI minus EI whole square. You can check over here 275 minus 242.1 whole square, the value is here. Then it is divided by 242.1 and you are obtaining it as an 4.471. In the similar fashion you can calculate all these values here and the total will speaks about your chi-square test statistic, that is your chi-square calculated value, where I have been represented here. Chi-square equal to summation Fi minus Ei whole square by Ei. Usually we will be using Oi or Fi, both will represent the same meaning here. The value is 40.937. Similarly, you have to move for your degrees of freedom here. The degrees of freedom will be 7 minus 1 minus 1, which minus 3, which will be equivalent to 2. Here with these degrees of freedom, you can go for your calculation, the tabulated value chi-square for 2 degrees of freedom at 5% level of significance. As I mentioned that the level of significance defaultly go with 0.05 or 0.01. Here you have been went with the 5% level of significance, and you got the table value as 5.99. Now we need to conclude. So you have to compare your chi-square calculated value with your chi-square table value. Now we can see your chi-square calculated value is 40.937 and your chi-square critical value or table value is 5.99. By comparing, you can understand that your calculated value is more than the table value. That's what you are concluding here. Since calculated value of chi-square 40.937 is much greater than 5.99, it is highly significant. So it means that it does not follow the Poisson distribution. Hence you can conclude that the Poisson distribution is not a good fit to the given data. So here you can see about that whether you are going to accept or reject the H0, the decision making has to be clear. That is, you may not commit any type 1 or type 2 error as mentioned in our previous classes. That is, while making a decision whether you are going to accept your H0 or you are going to reject your H0, you have to be concentrated whether you are making an right decisions, because which makes the impacts on our real time how you are going to work. Dear students, we come to the end of this lesson. We have been seen 3 different parts in this lesson. In part 1, we went with the categorical variables and its definition, and we have been went with the usages in our real time. Then we went with the computation of expected frequencies using distribution, and we have been fitted a distribution there. Then we went with the part 3. In part 3, we have been inferred the chi-square statistic, how we are going to make inferences on the Poisson distribution. I am confident that you understood all the concepts here and it will be useful for your research and in a future academic. We have come to the end of this lesson on chi-square as measure of discrepancy between expected and observed frequencies. Thank you.